So, we were discussing about application of first law, particularly the steady state form. You can see here the steady state form is written. This is the steady state form of first law, steady state form of the mass conservation with one inlet, one outlet. Okay. Steady state, steady flow. So, we will see now some application of these to some devices which are used every day or in our households or in the industry. So, the first and the easiest is probably, so the topic will be application of first law for open systems, for control volumes, for CVs. This is not curriculum vitae, this is CV, control volume, remember that. Okay. So, the first application that we will talk about is something, is the easiest one perhaps, it is nozzles and diffusers. Okay. So, all of you are familiar with nozzles and diffusers. These are not household items, usually they are not, but well, by the way, if you are using a hair dryer, then there is a nozzle there. Okay. So, in some cases it is, these are in household items, but usually they are used in industrial applications. So, for example, if you look at a jet engine which is attached to an aeroplane, we will see that there are both nozzles and diffusers. So, at the beginning there is a diffuser and at the end there is a nozzle. Okay. So, what do? They perform a very simple task, which is, I should probably take a different color, it is not working properly. So, if you look at a nozzle, what they do is, a nozzle typically looks like this. A nozzle looks like this. So, you have some inflow and usually the velocity is very small at the inlet, and then what it does is, by squeezing the fluid or by squeezing the area of flow, this nozzle speeds up the fluid, right. So, it takes in fluid which is flowing at a very small velocity and it accelerates it to a very large velocity. Okay. That is basically the purpose of nozzles. So, these are used wherever you need high speed liquid or air jets, or high speed jets of fluids. For example, in turbines these are used, in aeroplanes of course you need nozzles to create the boost. So, you need nozzles in many such applications. Okay. Wherever you need a fast jet of fluid. So, in nozzles you can see that it is an open system because there is inflow and outflow. Nozzles generally, so these are nozzles, by the way, let me write it down. So, nozzles generally are steady state devices, that means they usually operate at steady state. So, the mass comes in at a steady rate and mass flows out at a steady rate, and the conditions inside the nozzle does not change that much with time. If you are taking reading at a point inside the nozzle, you will see that the reading is not changing with time. So, this is a steady state device. So, steady state, okay. And you can see that only one inlet, one outlet in a nozzle. So, that checks out our the first law that we have written on the other side of the board, that is, it is compatible. So, one inlet, one in plus one out. Okay. So, let me call this m dot I, this can be m dot E, and in nozzle usually the processes are so fast and these are usually well insulated, so that the heat transfer is approximately 0, it can be well approximated as 0. The rate of heat transfer is approximately 0, and of course, this nozzle is not doing any work, it is not doing any non-flow work. You remember again, the flow work is there at the inlet and the outlet, but apart from that, it is not rotating any kind of shaft or it is not expanding against the an ambient pressure. So, the work done on or by the nozzle, non-flow work done, W dot Cv is equal to 0. Again remember, this is non-flow work. Okay. So, this is equal to 0. So, then let us see, write the first law and let us see what happens. Let me rewrite it maybe. So, we know that for nozzles you can write, we can write Q dot Cv minus W dot Cv plus M dot I Hi plus half Vi square plus Gzi minus M dot E He plus half Ve square plus Gze equal to 0. Mass conservation tells us M dot I is equal to, or rather M dot I minus M dot E is equal to 0. From this I can say that M dot I is equal to M dot E, which I can just call M dot, the rate of mass flow. This is the same as both the inlet and the outlet. Recall that this is the inlet and this is the outlet, this is I and this is E. So, now we can see which terms we can cancel out. So, this is, oh my god, it is not working. This is 0 as noted here, work done is 0. So, in nozzle what happens is the change in potential energy can be neglected. Okay. So, there is, I mean, even if there is some change in the potential energy, you will see that this is negligible as compared to change in the kinetic energy. Most of what a nozzle does is it takes a very slow moving fluid and converts it to into a very fast moving jet, and as a result there is a large change in velocity, but there is almost no change in the potential energy, right. I mean, of course, if this is horizontal, there will be no change in potential energy. Even if it is not horizontal, then also this change can be approximately neglected. You will see that this change is extremely small as compared to the change in the velocity. So, this I can write that probably delta V, the change in velocity is, or rather delta V square, the change in the kinetic energy is much larger than change in the potential energy. So, G delta Z. Okay. Delta V is the, so not delta V, maybe I should write delta Ke. So, delta Ke, the kinetic energy is much larger than, again I should write this, yeah, delta Ke is much larger than the change in potential energy. So, these terms I can safely just neglect. So, these two I can just neglect. Okay. Alright. So, these two are neglected, then what I have basically is, what I am left with is the following. Maybe I can write here only. So, I can see that I am left with the following. So, m dot times m dot times Hi plus half Vi square, capital Vi square, minus m dot times He plus half capital Ve square is equal to 0, which I can simplify. I can cancel the m dot from both sides. I can simplify and I can write that Hi minus He is equal to half of Ve square minus Vi square. So, this is true for a nozzle. So, what does it tell you is that, see, this is the change in kinetic energy. Okay. So, this term is delta Ke, and this term you can understand is delta H, change in enthalpy. Okay. So, there is a rise in kinetic energy. So, there is a rise in kinetic energy, Ve is much larger than Vi. Usually you can neglect this Vi with as compared to Ve. Okay. This will be very small and this will be extremely large. So, and they are squared also. So, you can neglect this term. Anyway, this is the change in kinetic energy. So, you can see that the change in kinetic energy is fueled by a drop in enthalpy, because this is positive, this has to be positive, which means H I will be larger than H E. So, at the inlet the fluid will have more enthalpy than the fluid that is going out, right. So, there is a drop in fluid's enthalpy which fuels its change in kinetic energy or in velocity. So, this is how a nozzle operates. You can let me take this opportunity to draw a diffuser. So, a diffuser is the opposite, right. So, you have a nozzle which accelerates fluids, a diffuser will be something that decelerates fluids. So, it will be something like this, something like this. Something like that, yeah. Diffuser will be something like this. So, where you have fluid that is coming in at a very large velocity. So, this will be your inlet, this will be Vi, and the fluid that is going out, it is going out with extremely small velocity. So, a diffuser slows things down. Okay. These are sometimes used in as I said, these are used in jet engines, these are also used in wind tunnel experiments, and there are many other uses, also used at the exit to the turbines and so on. So, anyway, these are used in many industrial applications, and so when there is an inlet, the fluid comes in at a very high velocity and it exits with a very small velocity. Again, this is a diffuser, let me write it down. Okay. Again, what happens is that you can see that there is only one inlet, one outlet. It is a steady state device. All the assumptions for a nozzle applies here also. So, Q dot and W dot, these are all 0, steady state device, one inlet, one outlet, which means that the same formula for that we derive for nozzle also applies here. Only thing is that here delta K is negative, because the velocity change velocity decreases, the fluid decelerates. So, this is negative. So, this will also be negative, which means I should write probably for a diffuser. So, this is for a nozzle. The same thing you can also apply for a diffuser, it is the same thing, but it is more convenient to write it by altering the signs, so changing the signs. So, for a diffuser we write H E minus H I is equal to half of V I square minus V E square. So, you can see that, so this is for a diffuser. So, you can see that for a diffuser there is a drop in kinetic energy, right, because V is less, V is actually far less as compared to Vi. So, you can practically neglect V, but anyway V, this delta, this is minus delta Ke, right, this is the drop in the kinetic energy, and that drop, what does that drop result in? So, you can see that that drop in kinetic energy increases the fluid's enthalpy. So, whatever drop is there in terms of kinetic energy, that same drop increases the fluid's enthalpy. This is what a diffuser is, it is just the opposite of a nozzle. Okay. So, this is so this ends our discussion on nozzles and diffusers. Please remember all the assumptions. Remember that if I for a moment come back to this diagram, remember that we are assuming that this nozzle does not exchange heat or work with the surroundings. So, work done is typically 0, that is not a problem, but this might be non-zero if, for example, this nozzle is large enough. Okay, then you might have to consider work, heat exchange, but for small enough nozzles or nozzles which are well insulated, this is 0. Okay. So, please remember those assumptions. Also remember that this is, we are talking about a steady state process, one inlet, one outlet, those things. So, it is very important to keep in mind the assumptions before blindly applying the formula. Okay.